Chapter 26 is about the z-test for the average. So first, let's do a little motivation for our z-test for the average. So in this example, we're interested in knowing if the average credit card debt for all Utah college students is less than $3,000. And we believe that the population standard deviation is 195. So first, how could we estimate the average credit card debt for all Utah college students? Now notice we're trying to estimate it for all the Utah college students. But we probably don't want to interview all of the Utah college students. That would take too long. And so we'll probably pick a sample and find the sample average. And then we'll use the sample average to estimate the population average. So the sample average is our best guess for the population average. So number 2, we want to conduct a hypothesis test to see if the average credit card debt for all Utah college students is less than $3,000. So let's write down our null and alternative hypotheses. The null hypothesis. Null hypothesis, status quo, nothing interesting. Remember, I also said it will be a definite statement, so it will always be an equals to, not a less than, a greater than, but an equals to. So the null then would be that the average debt for all the Utah students is $3,000. The alternative is that the average debt for all the Utah college students is less than $3,000. So once again, the null is kind of status quo, nothing interesting. The alternative is what we're probably trying to hope to prove, and we're trying to show that it's less than $3,000. So number 3, we're going to go through and kind of just do like some gut feelings on these. So we don't know anything technical yet, we're just kind of, what do we feel? So the question is, would you believe that the population average for all Utah college students is less than $3,000? If you found a sample average of 2,999. So remember, our sample averages aren't going to be exactly the same as our population averages. That's just due to a little bit of chance error. But we expect our population and sample averages to be close. So if I found a sample average of 2,999, that's very close to 3,000. And so I believe that my population average is 3,000. So specifically, no, I don't think that it's less than 3,000. So no, because 299 is very close to 3,000. So no reason to think that the population average is less than 3,000. What if you found a sample average of 2,000? Then would you believe that the population average is less than 3,000? Well, if I found a sample average of 2,000, 2,000 is really different from 3,000, and I think I would be really suspecting that the population average is less than 3,000. Because once again, a sample average of 2,000, that's very different than my hypothesis of 3,000. And so I would think that the population average is less than 3,000. I just want to add a little clarifying point here on A. Since 2,999 is very close to 3,000, I would say no reason to think the population average is less than 3,000. For C, what if you found a sample average of 400? Well, for sample average of 400, that is so far from 3,000. There is no doubt in my mind that the population average is definitely less than 3,000, because that sample average isn't even close to a population average of 3,000. Let's see, if I found a sample average of 6,000, well, 6,000 is really far from 3,000, but does it make me think the population average is less than 3,000? No. So that one's almost a trick question there. And for E, what if you found a sample average of 2,900? So we are off by a bit, but maybe not that much. I mean, the standard deviation is 195, so I'm not quite sure. And so for this one, I'd say I'm not sure. And how would you actually find out? Because my gut feeling isn't quite kicking in here. I don't quite trust just my gut feeling. I want something more mathematical. And to make it more mathematical, I need to calculate the standard error. And there's a question to you, would your gut feeling change based on the sample size? Well, it should, yes, because the sample size and standard deviation affect the standard error. And standard error is how much chance error we expect. So, since the sample size affects your standard error, how much chance error you expect, yes, that would affect my gut feeling. So to answer these kinds of questions, we do want to know what the standard deviation is and also the sample size so that we can calculate the standard error. So now for number 5, let's make it more specific. So let's say we took a sample of 50 students. We found a sample average of 2,920. Do you believe that the population average is less than 3,000? Oh, and don't forget that we already know our population SD is 195. Then at this point, let's think about a few things. So we said the z-test statistic is always our observed value. So z is always observed minus expected over the standard error. Now in this specific situation, when we're talking about averages, the value we observe is our sample average. And then we minus the expected value for the average over the standard error for the average. That would be the specific situation or specific formula for averages. So I need to know my sample average, my expected value, and my standard error. So let's go calculate those over here. My sample average, they told me, is 2,920. And then, what did you expect for your average? Well, usually for our average, we expect our population average. Now, I don't know exactly what my population average is, but remember for our null hypothesis, or we assume our null hypothesis is true for our calculations. So I'm going to assume that my population average really is that 3,000. So we're going to say it's 3,000. This is my hypothesized value. And then we need to find our standard error for the average. Remember, standard error is population SD over square root of the sample size. My population SD we said was 195 over the square root of our sample size. We took a sample of 50 students, so that's 50. And this gives me 27.6. So my standard error now is 27.6. We found a sample average of 2,920. We're asking ourselves, okay, would that be surprising? So to answer that, we need to know how many standard errors we were away from the expected value, or we need to find our z. So my sample average was 2,920, but I expected it to be about 3,000. And I know that my chance error is maybe about, or I'm expecting a chance error about 27.6, since that's my standard error. So let's put this in our calculator. We get negative 2.90. So this means that our sample average is 2.9 standard errors below the expected value. It's below because it's negative. And that would be surprising, because we expect to be within about 2 standard errors of our expected value. But I don't have to stop there. I can go and find the p-value. So here's z equals negative 2.90, and I'm looking for all the area to the left. So let's go to our normal table, look up negative 2.90, and that area is 0.19. Why did I do the area to the left? Because my alternative hypothesis is that the average that is less than 3,000. So values that are less, smaller values, give me more evidence against the null hypothesis. But in any case, this was 0.19%. So my p-value is 0.19%. This means that my null hypothesis that the population average is $3,000 does not seem plausible. So I conclude that the population average is less than 3,000. So once again, when you have a small p-value, your null hypothesis does not seem plausible, and you'll reject the null hypothesis, and now we can conclude that my population average is less than 3,000. So notice that we did all of this, and I haven't even introduced to you the specific z-test for average. We just did all of this based on what we learned in the introduction to hypothesis testing, just kind of by reasoning through everything. So now let's actually go on to the next page, and I'm going to officially introduce the z-test for the average. So we're going to use this test if we're interested in the population average, and we know the population standard deviation. And technically, as an assumption we need to check, we should only use this test, because we're trying to use the normal curve as part of the test, we should only use this test if the data is normally distributed, or the sample size is large, at least 30. The test statistic will always be z equals our sample average minus the expected value for the average over the standard error for the average. And just remember, the expected value for your average is your population average, and the standard error is your population SD over square root of the sample size. And as a note, the expected value, we need to know the population average, and we don't know for sure what the population average is, but for our calculations we assume that the null hypothesis is true, and so whatever your null hypothesis says the population average is, that's what you'll put for your expected value. So let's put this into play. So example 257, you know that nationally the average number of hours that parents read to young children is 0.7. You feel like your neighborhood is excelling in this area, so you take a simple random sample of 10 households. So my sample size equals 10. The average is 1.3. Now notice that's the average for my sample, so that's my sample average. Equals 1.3. Suppose the SD of the neighborhood is 0.3 hours. And that reading times are normally distributed. So we care about the fact that it's normal here, because that was a small sample size. My sample size was less than 30, so I can only use the z-test because it told me that the data is actually normally distributed. So So my null hypothesis is going to be that the average reading time for all children in the neighborhood is what? Let's see. So you have to kind of read in between the lines here. So it says, we think that our neighborhood is excelling in this area. So I would say, sometimes it's easier to write the alternative first. The alternative here is that we think that the average reading time for all children in the neighborhood is, I would say, more than the national average of 0.7. Specifically because it said we think that they're excelling, and so the alternative is we would want to show that the average time for all the children in the neighborhood is more than 0.7, which means that my null hypothesis would then be that the average reading time for all the children in the neighborhood is 0.7 hours. Once again, sometimes it's easier to write the alternative since the alternative is what you're trying to show, and then I just come back and fill in the null. Okay, now let's find our test statistic. So remember, we need to find our expected value and standard error, and I've written in the formulas for us. So my population average, I don't know what it is, but we assume the null is true, which would mean that my population average is 0.7. For the standard error for the average, the standard deviation was 0.3, and the sample size was 10. So 0.3 over the square root of 10 is 0.0948. Now let's find our test statistic Z. It's going to be my sample average minus the expected value divided by the standard error. My sample average was 1.3, but I expected it to be 0.7, and the standard error is 0.0948. Let's put this in our calculator, 1.3 minus 0.7, and divide all of that by 0.0948. So this gives me 6.33. That's a really big Z value. So we're 6.33 standard errors from the expected value. That would be very surprising. Let's go on though and see how surprising that is exactly by finding our p-value. Here's my Z equals 6.33. Now let's go to my normal table. Well, first, which direction do I want to shade? My alternative hypothesis is that the average is more than 0.7, so because we're looking for more than, we're going to want to shade to the right. So let's go to our normal table. Now the highest this table goes is Z equals 4.44. So if you were to kind of continue, I would say by the time at 4, the area to the left was already 99.99. I would say by the time we get to 6, it's basically going to be about 100. And if the area to the left is about 100, what's the area to the right? Well, about 0. So the area to the left is about 100. So the area to the right is about 0%. So my p-value is basically 0%. That's very, very small. What this means for us is if the null hypothesis is true, so basically if the population average is 0.7, then there is only well, 0% chance of getting a sample average of 1.3 or more. So there's something wrong here, right? Because we know that we got the sample average of 1.3. So that means my assumption that the population average was 0.7 was wrong. So, does the null hypothesis seem plausible? No, absolutely not. So in conclusion, we had a small p-value, very, very, very small p-value, so we will reject the null hypothesis, and we conclude that the population average reading time for all the children in the neighborhood is more than 0.7 hours. We don't actually say how big we think it is, just that it was more than 0.7 hours. So let's try our next example. Bottles of orange juice are supposed to have 16 fluid ounces. Someone suspects that the bottles aren't full enough, and they take a random sample of 100 bottles from a large batch that contains an average of 15.9 ounces. From past experience, the standard deviation of all the bottles is 0.2 ounces. Test the hypothesis that the bottles are being filled correctly against the alternative that they are not full enough. So let's write down what we're getting here. So bottles of orange juice are supposed to have 16 fluid ounces. So I would expect my average to be 16 ounces. Or that's kind of my hypothesized population value. But someone suspects that the bottles aren't full enough. They take a random sample of 100, so that'd be my sample size. From past experience, the standard deviation of all the bottles is 0.2. So my population standard deviation equals 0.2. Test the hypothesis that the bottles are being filled correctly against the alternative that they are not full enough. So the null hypothesis is that they are filled correctly, or that the population average is 16 ounces. The alternative hypothesis, they said that they are not full enough, so that would mean my population average is less than 16 ounces. So for my test statistic, first I need to find the expected value and standard error. The expected value is my population average, and I don't know what that is, but we're going to assume that the null is true, which means then it would be 16 ounces. The population SD is 0.2 over the square root of my sample size, which was 100. So 0.02. Now let's find our test statistics. So Z equals my sample average minus the expected value for my average, divided by the standard error for my average. So my sample average was 15.9. The expected value was 16. The standard error is 0.02. So this is going to give me -5. So we're 5 standard errors below our expected value. That's more than 2 standard errors. That means it's surprising to me, and very surprising to me, because that's 5 standard errors is a long ways. Now let's find the p-value. So because we're looking for the population average as less than 16 ounces, we're going to look for the area to the left, left for less, the left of Z equals -5. So here's Z equals -5. We're looking for the area to the left. This is very similar to our last example in that if I come and try and find -5, it's not on the charts. -4 is as far as we go, but if we kind of go up a bit and continue the pattern, by the time we get here, I think that area to the left is going to be about 0. So when numbers are so far off the charts, we're just going to say it's about 0. So the p-value is basically 0%. So this means if the null is true, so basically the population average is 16, then there is only a 0% chance of getting a sample average of 15.9 ounces or less. That is a very, very small chance. So I don't think the null hypothesis of the average is 16 is plausible. In fact, not only do I not think it's plausible, I'm quite certain that it is not plausible. So, does it seem plausible? No, absolutely not. So in conclusion, we had a small p-value, 0% is very small, so we'll reject the null hypothesis. You always reject the null hypothesis if you have a small p-value. Okay, and we conclude that the population average is less than 16 ounces. So they're not filled enough. And since that p-value is so small, we have lots and lots of evidence that the population average was less than 16 ounces. Now I have a bit of a caveat for you of we found evidence that the average of all the bottles is less than 16 ounces. But maybe a more important question is how much less? So the sample average of 15.9 ounces, that would be our best guess of the true population average. But 15.9 ounces isn't much smaller than the expected 16 ounces. And so that probably won't make much of a practical difference. Like for me as a consumer, I would never notice if they cheated me out of 0.1 ounces. And so it probably doesn't make that practical difference. And so hence we learned that statistical significance does not always mean practical significance. So let's write ourselves a little note that statistical significance means that we have a small p-value. It means that we're very sure statistically that there is a difference. Practical significance means doesn't matter in real life. So once again, we are very sure, statistically speaking, that there was a difference here, that the average of all the bottles was less than 16 ounces. But practically significant means, does it actually matter in real life? So does anyone care if they're off by 0.1 ounces? And to answer that, you have to actually be an expert in the field that you're interested in. And so maybe being off by 0.1 ounces, maybe that would matter to consumers. Maybe it wouldn't. What if, think about it in the other direction though, what if they were giving all the consumers an extra 0.1 ounce? That might not matter for 1 or 2 consumers, but what if they were doing that for thousands of bottles? Eventually that price is going to stack up, and so to those people, then yes, that might be practically significant. So once again, does it matter in real life? That would depend on what you're talking about, and you would need to bring in the expert in that field. For our next example, suppose that we gather a random sample of 50 Utah high school students who took the SAT in 2006 and found that for this sample the average math score was 523. Suppose the standard deviation for the state was 25 points. Is this evidence that the average SAT score for a Utah student is higher than the national average of 518. Let's first go through and write down our information. So we had a sample of 50, so my sample size equals 50. For this sample, so my sample average equals 523. Suppose the standard deviation for the state was 25 points, so my population SD equals 25. Is this evidence that the average SAT score for a Utah student is higher than the national average of 518? So we are comparing to 518. My null hypothesis would be then that the average of all Utah students is 518. So remember, status quo is just that you be equal to whatever you're comparing to. So 518. The alternative is that the average of all Utah students is which direction? So they want to know, is this evidence that the scores for Utah is higher than 518? My alternative is that we're higher than 518. Now for our test statistic, the expected value is our comparison of 518. Of course, the average in your null hypothesis. The standard error is going to be my population standard deviation of 25 over the square root of the sample size, which was 50. And this gives me 3.54. So Z equals my sample average minus the expected value divided by the standard error. My sample average was 523, but I expected 518, and the standard error is 3.54. This gives me 1.41. So we are 1.41 standard errors from the expected value. So that is not surprising. So maybe the null hypothesis is going to be plausible. Okay, now let's go on and look at our p-value to be sure. So for my p-value, we go to Z equals 1.41. We're looking for the area to the right because we're trying to show that our scores are higher than 518. So let's go to our normal table. We're looking for Z equals 1.41. The closest is this 1.4 for an area of 91.92. But that's the area to the left. So we'll do 100 minus 91.92, which gives me 8.08%. So my p-value is 8.08%. And what does this mean for us? This means that if the null is true, so in other words, if the Utah population average really is 518, there is an 8.08% chance of getting a sample average of 523 or more. Now 8%, that might not seem very high, but 8%, that's about like 1 in 12, so it would happen fairly often. That's not a horrible chance. And so when I ask, does the null hypothesis seem plausible, I would say, yes, it seems plausible. I can believe that an 8% chance happened. That's not that big of a stretch. And specifically, .08% is bigger than 5%, which is our cutoff. So for our conclusion, because we had a big p-value, we will fail to reject the null hypothesis. Now, we haven't really talked about why yet, but this is how you actually have to write your conclusion. You're going to say that we don't have enough evidence to say that the Utah population average is higher than the U.S. average of 518. So it's interesting that we kind of changed the way we're writing it. So you always write the conclusion in terms of the alternative hypothesis, because that was what we're interested in showing. And so your conclusion will always be either we have evidence of the alternative or we don't have enough evidence for the alternative, because once again, the alternative is what you're interested in proving. And here's a little note that kind of ties into that. So failing to find evidence against the null hypothesis, like in this situation, only means that the data is consistent with the null hypothesis. It doesn't actually mean that we have clear evidence that the null is true. So that's why, in this case, we didn't say we conclude that the population average is 518. We say that we don't actually have enough evidence to say that it's higher than 518. So as an example of this, people in England, whenever they would see swans, the swans were always white. And they saw millions of white swans, and they believed that all swans were white. However, when they went to Australia in, I think, the 1600s, they found black swans. And all it took was one black swan to disprove their theory they'd had for hundreds, if not thousands of years, that all swans were white. And so this is kind of one of those things of, we've said, okay, the data seems consistent, so all the swans seem to be white, so it seems consistent with the hypothesis that swans are white. But it doesn't actually mean for sure that we have evidence that the null is true. Okay? We just didn't find evidence against it. Okay. So on this next page, let's write ourselves a note that the real-world conclusion is always in terms of the alternative hypothesis. I know that seems slightly strange at first, especially because we spend so much time talking about the null, but remember, the alternative is what we're hoping to show, so our conclusion will always be in terms of the alternative. Let's talk a little bit about rejecting or failing to reject the null hypothesis. So a hypothesis test only rejects the null hypothesis if there's strong statistical evidence against it. So this is similar to our legal system. We declare someone guilty or reject their innocence only if the evidence of guilt is beyond reasonable doubt. Due to convention, just tradition, if our evidence isn't strong enough to convince us to reject the null hypothesis, we do not say we accept the null. Instead, we say we fail to reject the null, or we don't have sufficient evidence to reject the null hypothesis. This is like the legal system. If we don't have enough evidence to prove that a person is guilty beyond a reasonable doubt, we pronounce him not guilty. We don't say that we have proved his innocence. So just as a note, if you were to try and write the null and alternative hypothesis for this situation, the null hypothesis, the status quo, would be that he is innocent. Because you're innocent until proven guilty, that's your status quo. Then the alternative is that you're guilty. And then to reject the null, to reject the fact that you're innocent, you have to have evidence beyond reasonable doubt. So you have to have a lot of evidence against the null, and then you can say they're guilty. If you can't reject the null, then we still phrase it in terms of the alternative and just say not guilty. Now let's talk briefly about a two-tailed versus one-tailed test. So if we have a suspicion before we do the experiment or take a sample that the alternative hypothesis will only be in one direction, we do a one-tailed test. So this is an example, like if the average of the box is 25, the alternative could be, say, that the average of the box is less than 25. So if we're interested in the average being less than 25, we're going to find our z-value and shade to the left because it's a less than, so we shade to the left. And this is what we've been doing so far. But sometimes we're interested in seeing if the average is more than 25. So then you find your z-value and you shade to the right because it was more than. But sometimes we don't know in advance which direction we're interested in going. So we don't know if we think the average is bigger or smaller than a certain value. And so instead we just say the average is not 25. And in this case, what you actually have to do is you find the z-value and you use symmetry and find both tails. So maybe you have a positive z, maybe you have a negative z, but you're going to find the average or the area in both tails. And just as a note, it might be tempting to look at your data and then write the alternative hypothesis, but ethically speaking in statistics, we're not supposed to do that. We're supposed to pick the hypotheses before we compute anything for the hypothesis test. Because before you go out and look up data, you are supposed to already have some kind of hypothesis in mind that you want to test. So let's try an example. In this example, the average weight of lab mice is about 30 grams and the standard deviation is about 5. At a particular lab with hundreds of mice, graduate students took a sample of 15 mice, and the average weight of these animals was about 33. So my sample average was the 33 because it was the average for the mice in this lab, in this sample. My sample size was 15. Now it says we will use the standard deviation of 5 for all the lab mice as the standard deviation for our population of mice at this lab. So the question is why? Well, if you might have noticed on these, we're saying that we have the population SD. But the question is always, well, if you have the population SD, you would have to know everything in the population. And if you know that, why don't you just calculate the population average? So in real life, we usually don't know the population SD, but sometimes in situations like these, we can reasonably guess what it might be. So in this case, a good guess for the standard deviation for all lab mice in this lab is that it could be the same as the standard deviation for all lab mice everywhere. So our population SD, we will estimate as 5. Because once again, the SD of all mice everywhere, all lab mice everywhere, is the best guess for all mice at this lab. So even though we don't know for sure what our population SD is, we can estimate it with the SD of all lab mice everywhere, and that's a fairly safe estimate. Okay, and then is the weight of the mice at this lab significantly different from the general lab mice? Notice that they don't say we think that it's higher or we think that it's lower, it just says is it different? Okay, in this one I haven't given you the steps, so we're going to need to just do them on our own. So the first is write your null hypothesis, and that would be that the average of all mice at this lab is 30 grams. The alternative hypothesis is that the average for all mice at this lab is not 30 grams. So once again, we don't know if we think that it's higher or lower. We just want to know if it's different from 30 grams. So once I have my hypotheses, the next step is my test statistic. For my test statistic, I need to calculate the expected value of the average. So that's equal to your population average, which we're hypothesizing is 30. The standard error for your average is equal to your population SD, which we're estimating as 5, over the square of the sample size, which was 15. So this gives me 1.29. And then my actual test statistic Z is going to be my sample average minus the expected value for my average over the standard error for my average. So my sample average was 33, but I expected an average of 30, and my standard error was 1.29. So this gives me 2.325. Now let's find the p-value. This is going to be the area in both tails, because my alternative hypothesis is just that the weight is not 30 grams. We didn't say if it's higher or lower, so we just have to look at the area in both tails. So here is Z equals 2.325, so we'll shade to the right, and then we'll go over to the symmetrical tail of negative 2.325 and shade to the left. Now this area to the left, that one's easier to look up on the normal table. So negative 2.325 let's see, 325, looks like it's in the middle of these two values, so I'll just pick one. I'm going to pick this one right here and say that that area to the left is 0.94. Now due to symmetry, this area to the right is also 0.94%. So my p-value is 0.94% plus 0.94% because it's the total area in both tails. So this is 1.88%. Now, this is a small p-value. Specifically, it's smaller than 5%, which is our cutoff. So we will reject the null hypothesis and we conclude that the average of all the mice at this lab is not 30 grams. I don't know if it's higher or lower or what it is, but I have evidence that it is not 30 grams. And just as a note, as it turns out, the weights of the mice are normally distributed. But if the weights hadn't been normally distributed, would our results for this test still be accurate? So this would be no, because the Z-test requires normal data or a large sample size of at least 30 is our rule of thumb. So since we had a small sample size of what, 15? We can only do this test if the data is normally distributed. So usually you should check that before you actually do all of your computations. And for a final bit of theory, when we reject the null hypothesis, we have evidence that the alternative hypothesis is true. But keep in mind, we haven't actually proven it for sure. Because we're dealing with chance, you can't know which hypothesis is correct for sure. Now in this situation, our p-value was 1.88%. This means that if the null hypothesis was true, meaning that the average of all the mice at this lab was 30 grams, then the chance of getting a sample of 15 mice with an average of 33 grams or more is only 1.88% chance. So that's a small chance, but it's not impossible. 1.88, that's happening about 2% of the time. That's about 1 in 50. So it's not impossible. So the null hypothesis might still be true, but it seems very implausible.